Hi everyone, welcome to my calculus lecture. In this lecture, we study optimization problems. In many practical problems or like real life problems, we try to find the maximum or minimum of certain quantities. So we are going to go over some of those examples in this lecture as applications of the first, and also the second derivative test we studied in my earlier lecture. So here comes the first example. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a stray river. He needs no fence along the river, and in that case, what are the dimensions of the field that has the largest area? Okay, so that has the question. This type of questions, okay, uh, you know, often it helps to set up the question if you draw a picture that depicts, the question, okay, the description of the question. So, right. So this side is a river. Okay, so that's river where you don't need the fencing. So the fencing, required fencing, is drawn in the green color. Okay, so let me call the length of this rectangular field x, and I'm gonna call the width of this rectangular field y. Okay, so in that case, the fencing, well, fencing is actually the length of fencing is the length of this rectangular field, right? So, in terms of x and y, that's going to be 2x plus y, okay? And according to question, that's 2,400, right? That is 2,400 feet, right? 2,400. So this type of condition is called a constraint. When you work on optimization problems, right? So optimization problems often come with the certain constraints. So what this constraint does is it helps us, right? It allows us to reduce, in this case, what we have two variables involved, right? In order to uh, solve the problem, we have to deal with we have to have a function of one variable, like the function that we want to maximize or minimize. So in order to apply like the first or the second derivative test, we have to have a function of one variable. And in fact, this type of problems, the although we have two variables, but due to the constraint, right? Those two variables are actually having a functional relationship. So one variable can be solved in terms of the other variable. Right, just like this case. So, we can actually solve this for y. So y is going to be 24. Something is not right. Okay, I didn't write this correctly. Sorry. Actually, what is that? Uh, the fencing is x plus 2y, right? X plus 2y. Yeah, okay, so that's incorrect. Right, so x plus 2y, that's correct fencing. So if you solve for y, do we have to solve for y, by the way? You don't have to. You can solve for x, and then, in that case, you will end up getting a function of y. So it works, one way or another, right? But in my case, I prefer to have a function of x, all right? So, I'm going to solve this equation for y. So we are going to have y equals 1200 minus, x over 2, okay? All right, and what is the question? Again, let's go back. Okay, so the question is, what are the dimensions of the field that has the largest area? So here, largest area means that we are maximizing. Okay, we are maximizing the area. Okay, so keep that in mind. So area is the quantity we are looking at. So I am going to write down an area function, okay, area function, right? This is a function of x, and area of this field is going to be given by x times y, right? So x times y, but instead of y, I'm going to use this one here. So 1200 minus x over 2, which equals 1200x minus x, this is x, right? So x squared over 2, okay, x squared over 2. All right, so we are maximizing, okay, we are maximizing, meaning that we have to, so what is that? What we have to find out is the dimensions, right? Dimensions. So x value and y value, length and width, that give rise to the largest possible value of the area, meaning we have to find the derivative of a. So that the dimension will be given by the critical points, right? Critical points. So we take the derivative a prime of x. Okay, that's going to be 1200 minus x, right? 1200 minus x. So set that equal to 0. So we have x equals 1200. All right. Now, so we have a question. Actually, the a prime of x, right? So by setting a prime of x equals 0, you find the critical point. But how do we know that? Actually, know that that x value is in fact, gives rise to a maximum, okay, maximum value of a of x, or in other words, largest area, right? So that's where we don't know at the moment, but that's where the second derivative test comes in. Okay, so let's find it. The second the second derivative. So a double prime of x, in this case, a double prime of x is going to be just a -1. So this is always negative, regardless of what x value is there, always -1, which means that, a of 1200, okay, as not only actually, so that means what? The a of x, the graph of a of x is always concave down, always concave down. So in fact, a of 1200 is not only a local maximum, it is actually the absolute maximum. Okay, it is the absolute maximum. So this is going to be the absolute maximum. Okay, so therefore, the desired the desired dimensions is going to be 1200 length times width. Okay, so 1200, and y is given by 1200 minus x over 2, right? So 1200 minus x over 2, that's going to be 600. So that's going to be, yeah, so y equals 600. So 1200 feet times 600 feet, that is going to be the, and that's the desired, dimensions. In fact, in this case, the the largest possible area, which is a over 1200, that can be also calculated, right? And that's going to be 720,000 feet squared. Okay. No, that's incorrect. 720,000 square feet. Okay, but actually this is the required answer. All right, so let's move to next example. Now, so next example is the following. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Okay, so here there's typo, okay, supposed to be cubic centimeters. Right, so find the dimensions of the box that minimize the amount of material used, okay, the material used. Okay, so in this case, let me draw a picture. Okay, so you know that the base is square, right? So let's call this x accordingly, or where this is also x, right? Length and width, they both are same as x. And then the height, I'm going to call this h. Okay, right. So the volume is given. Okay, the volume is given. What does it say? Must have a volume of 32,000 cubic centimeters. Okay, cubic centimeters. So here's the volume, which is given by x squared times h. That has to be 32,000 cubic centimeters. Okay, I'm not going to write down the unit. But you know, as you can notice, this will give us, I mean, this is going to be a constraint, right? Constraint, and then this will allow us to reduce, you know, two variables are also involved in this case, x and h, but it's going to allow us to reduce them to one variable, right? In this case, I'm going to solve this volume for h, so that gives us 32,000 divided by x squared. And what we are trying to minimize, right, in this case, minimize the area, okay? Find the dimensions of the box that minimize the amount of material used, right? The amount of material is same as the area of the box, the surface area of the box, okay? So the surface area, I'm going to use the a of x, right? So that's going to be, what is that? The bottom part is x squared, right? And then we have four lateral surfaces, okay? So, you know, each of them, each surface, right? Lateral surface is given by x times h. So we have four of them, 4x times h, but instead of h, I'm going to use this. So 32,000 divided by x squared. Okay, so this one here is a surface area, which is also same as the amount of material, okay, the amount of material used to make this box. Okay, so we have this is gonna be x squared plus 4 times 32,000. That's going to be 128,000 over x. Okay, so we are trying to minimize, right? So we try to minimize this. Right. So again, we have to find a prime of x, okay? We're gonna find the critical point. So a prime of x, in this case, that's going to be 2x minus 128,000 over x squared, and then set it equal to 0, okay? Set it equal to 0. So from this, we get an equation, right? X cubed minus 64,000, right? 64,000, okay? Equals 0. So that's going to be, now notice that 64,000, that's going to be 40 cubed, okay? That's 40 cubed. So x equals 40. So this equation has only one real solution, which is x equals 40 centimeters. All right. Now the thing is to determine, we have to determine that this x equals 40 actually minimizes, the a of x. Okay. In other words, the a of 40 is going to be absolute minimum. For that, we are going to use the second derivative test. So we find the second derivative, a double prime of x. Okay? So a double prime is going to be 2 plus 256, okay, 256 thousand over x cubed, okay, x cubed. This is gonna be always positive for all x positive values. The x is what the length, okay, length and also width of the box, right? So of course, it is always positive value. So regardless of what x value is, right, a double prime of x is always positive. Meaning, this means that by the second derivative test, right, by the second derivative test, a a of what the value I found, right? 40. It was 40, right? A 40 is the absolute minimum. Okay, absolute minimum. Okay, that's going to be the absolute minimum. So the required, therefore, the required dimensions are 40 centimeters times 40 centimeters, and the height h is what? H is 32,000 divided by x squared, right? So that's going to be 20 centimeters. Okay, 20 centimeters. Okay, so that's going to be the desired, uh, the required dimensions. Good. Okay, so let's move to next example. Okay, so here's the next example. If 1200 square centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of the box. Okay, so we actually have the same type of box as like in the previous example, but in this case what we have here is the limited amount of material, and we try to make a box. We try to figure out the like I say dimensions. Okay, we try to find the dimensions that give rise to the largest possible volume of the box. Okay, so that's the question. So I'm going to draw the same box I drew earlier. Okay, so let's call this length and width is a square base. So let's call them length and width. X, right? And the height is going to be h. Okay, so we have limited material, which is 1200 square. I forgot the unit. It's just like a square centimeters. Okay, right. So we have this is our constraint, x squared plus 4 times xh. Okay, that equals 1200. Okay, that's 1200. So this allows us to solve, right? I mean, for h, right? So h is going to be in terms of x. That's going to be 1200 minus x squared all over 4x. Okay, which equals 300 over x minus x over 4. And we want to maximize the volume. So we consider a volume function, which is a function of x. So volume is x squared times h. So x squared times h, but instead of x, I'm gonna use that guy so that we can have we can write down the volume as a function of a single variable x. So x over 4. Good. And so that equals 300 times x minus x cubed over 4. Okay, so to maximize this volume, we find the derivative, so v prime of x, right? So that's going to be 300, right? Minus 3x squared over 4. So we are going to set this equal to 0, okay, equal to 0. So, that's gonna be, right, so if you divide, multiply each side by, what is that? What do you have to do? Multiply by 4 thirds, right? So that's going to be 400 equals x squared. So that's what we have here. 400 is 20 squared, so we find x equals 20, right? I mean, x has to be positive, so we have only one solution. X equals 20 centimeters. Okay, right. So that's critical point. We have only one critical point, but why does that, maximize I did something and it became smaller. So I don't know how to make it big. Oh, maybe this. Oh, wonderful. Okay, so, oh, that's too big. All right, that looks all right. Okay, yeah, yeah. I panicked a little bit. Okay, but that's x is going to be 20. All right, that's what I have. I think I see like a little edge here, so I'm gonna make it like a little bigger. Made it too big. Okay, so come on, little bit, little more. Um, go back. Yeah, I'm gonna leave it like that. Okay, so yeah, that's all right. So x equals 20. Okay, so I was saying earlier that in order to uh, make sure that x equals 20 gives rise to the maximum volume, we will have to use the second derivative test, right? So let's find the second derivative of the volume function. So what happens? This is constant, right? This is constant, and that's going to be negative, the 3 times No, actually 6 over 4, right? 6 over 4. Six over 4, which is actually 3 over 2. So 3 over 2x, right? Now x is positive, so regardless of what x value is, x is always positive. So due to this negative coefficient, this is always negative for all x positive value, right? This means that the graph of v of x, the volume function is what? Is always concave down, concave down. So that means by the second derivative test, I'm not going to write it down, but v of 20 maximizes, okay, maximizes. Actually, in this case, we don't, the question is just find the maximum volume, not the dimension, although like, dimension you can easily find out, but the v of 20 equals 4,000 cubic centimeters. Okay, that's going to be is the largest possible volume. Okay, largest possible volume. I think this is a good point to stop, and we will continue to go over more examples in my next lecture.